Hey guys, one more video for today. We're going to apply the mass explosion concept I covered in the last video to a neutron undergoing radioactive decay. Here's what happens. We're going to start with our neutron that's just hanging out by itself and not moving. The decay will occur, and from that we get a proton and an electron moving in opposite directions. Our goal is to figure out the fraction of the total decay energy that the proton receives. The process of doing that is almost identical to the way that we did problem number 9 in this chapter. First, we start with the conservation of momentum. It's 0 on the left, since the neutron wasn't moving, and then there's the opposite momenta of the proton and the electron on the right. We want to move the proton's momentum over to the other side and then solve for the velocity of the electron by dividing both sides by the electron's mass. This will allow us to express the kinetic energies in terms of the proton only. Here's the conservation of energy following the decay, where the sum of the kinetic energies is equal to the total energy that was released. Let's plug in the expression for the velocity of the electron, and then we'll square the quantities inside the parentheses and cancel out a factor of the electron's mass in that second term. Following that, we can factor out 1/2 the mass of the proton and the proton's velocity squared to put the proton's kinetic energy outside the parentheses. Go ahead and divide both sides by the remaining stuff inside the parentheses and multiply 1 in the denominator by a special factor of 1. Now we can combine the fractions down there. Just like in problem number 9, we're going to multiply Q by the reciprocal of the fraction found in the denominator, which flips it right side up. And now we have a proper expression for the kinetic energy of the proton. In the problem description, we were told that the mass of the proton is 1,836 times larger than the mass of the electron. Let's plug that into what we have. The mass of the electron can be divided out completely, and from there we can continue using pure numbers inside the parentheses. Add the values in the denominator, and you'll find that the proton inherits a super tiny amount of the decay energy. Expressed as a percentage, it's a mere 0.0544% of whatever Q happens to be, and the remaining energy is gobbled up by the electron. That's it for now. Our problem is now done. Have a great day, folks. See you in the next one.